Correlation is the measure of the direction and strength of quantitative data. Correlation shows how linear the relationship is. The more linear, the stronger the relationship. This is indicated by an R value in between positive or negative 1.
A correlation coefficient, or an R value, of 1 indicates a perfect, very strong positive correlation. An R value of 0 reveals no relationship. An R value of negative 1 indicates a perfect, very strong negative correlation. We describe correlation as strong, moderate, or weak, and as positive or negative.
The first step to calculating the correlation coefficient is to calculate the orientation of each point in respect to the mean.
X bar represents the mean of the X data, while Y bar represents the mean of the Y data. Subtract X bar from each X point and Y bar from each Y point in order to get the orientation of each point in relationship to the mean. In order to combine the orientations of each point, multiply the X orientation by the Y orientation. This gives you the point's combined orientation. Then take the sum of each point's combined orientation and divide by the number of points in the dataset in order to get the mean of each point's orientation of the dataset, which is also known as covariance.
The denominator of the correlation coefficient calculation is the standard deviation of the X data multiplied by the standard deviation of the Y data. If the data is very spread out, the standard deviations, and therefore their product, will be larger. A larger denominator makes the R value closer to 0, and therefore the data is less linear. If the data is not very spread out, the denominator will be smaller, and the R value will be closer to 1 or negative 1, and therefore more linear.
After dividing the covariance, which shows direction, by the product of the standard deviations, which shows linearity, our final equation for determining correlation coefficient is
Chi-squared is a statistical way to determine if data sets are off due to chance or due to a dependent relationship. The chi-squared test tests this by measuring the difference between the theoretical, perfect probability, expected results or values, and the actual data, observed results or values.
The first step is to categorize the observed results. If the data does not self-categorize, use the mean to divide the values. Do not manipulate the data by using something not natural to categorize. If any category contains fewer than 5 values, the test will not be reliable, so recategorize if necessary. Mark each X value and Y value as above or below the mean, or whichever point you are dividing at. Tally the data that fits into each quadrant, taking the X orientation and Y orientation both into account, and record the subtotals. This gives you the frequency of observed values.
Calculate the probability of each row and column. To find the probability of any particular quadrant, multiply the probability of that row by the probability of that column. Multiplying the two probabilities gives the expected probability of each quadrant. In order to find the expected results for each quadrant in terms of your data set, multiply the calculated expected probability for that quadrant by the total number of values. This gives the data distribution for each quadrant if the data were to be perfectly independent. By comparing the frequencies of expected values to the frequencies of observed values, we can see if the data is independent.
A smaller difference between the frequency of expected values and the frequency of observed values results in a smaller chi-squared, meaning that the data is closer to independence. If chi-squared equals 0, then the data is truly completely independent. In order to calculate chi-squared, subtract the expected frequency from the observed frequency. In order to avoid negative differences between frequencies from canceling out positive differences between frequencies, and to clarify the difference between the expected and observed, square the difference. Then, to put the squared difference in context of the dataset, divide it by the expected value. Finally, take the sum of all these values in order to calculate chi-squared.
The chi-squared value determines independence at different levels of certainty. Using the table of critical values of chi-squared, compare the chi-squared value within the row of appropriate degrees of freedom. Degrees of freedom is calculated by the number of rows minus 1 times the number of columns minus 1. If the chi-squared value is between 0 and the value listed in the column labeled 0.9, then we can be 10% certain that the data is independent. If the chi-squared value is between 0 and the value listed in the 0.95 column, then we can be 5% certain that the data is independent. If the chi-squared value is between 0 and the value listed in the 0.99 column, then we can be 1% certain that the data is independent. If the chi-squared value is above the value listed in any column, we can be certain that it's dependent to that level of certainty.
You can go.
Wait, there's a person coming.
Okay. Okay, now I'm ready again.
Okay. Tell me when to start.
Start. Start!
Attention to the group.
Okay, go.